This is Physics 2212 Lab 6, which is magnetic molasses. The purpose of this lab was to observe a magnet falling through the tube of aluminum foil, model its behavior, and compare the experimental and computational results. So our experimental average fall time was 1.296 seconds, and our computational fall time was 0.555 seconds. Key concepts that we used in this lab were Faraday's law, which says that the EMF is equal to the derivative of the magnetic flux with respect to time. The Biot-Savart law, which gives the magnetic field of a particle. Newton's second law, which says that the force is equal to mass times acceleration. Newton's third law, which says that the magnitudes of forces should be equal to each other. And Lenz's law, which adds on a negative to Faraday's law and says that the EMF is the negative of the change in flux with respect to time. So for the experiment, our system was the magnet, and the source is the tube and Earth's gravity because they exert forces on the magnet. And to the right, you can see our experimental setup. We just held the foil tube above the table and dropped the magnet through. So we dropped the magnet through the tube a total of 5 times, recording the time between the magnet entering and exiting the tube. And then in the table are our exact results, and then our average fall time was 1.296 seconds. So here are some images of my coding. Image 1 at the top is adding the measured values for length, width, and the radius of the foil tube into the program. Image 2 is adding the measured and calculated values for the mass of the magnet and the dipole moment. The dipole moment we found in lab 4. Image 3 is creating a function for magnetic field of the bar magnet. Image 4 is calculating the derivative of the flux with respect to time. Image 5 is calculating the current in the ring. Image 6 is computing the B field at each ring, and image 7 is calculating the magnetic force. Here is the code output. As you can see from the graph, our magnet starts off with a pretty speedy velocity, and then it eventually flattens out before it gets to the end of the tube. So the checkpoint questions from the lab were, why can't we use a ferrous tube? And the answer to this is because the magnet would be attracted to and stick to the tube since it's magnetic. And then what happens to the magnet? How does this compare to the magnet falling in free space without a tube? So the tube is conductive, meaning a changing magnetic field will induce a current that opposes the falling motion. And so this will slow down the magnet. And then in free space, this wouldn't happen because you wouldn't have the force, so slowing down the magnet, you just have the gravitational force. So the computational result is a little less than half of the experimental result, and potential sources of error that could account for this is human error in calculating the time interval, or if the magnet hit the side of the tube and created some friction that we didn't account for. And there could also be human error in starting and stopping the video at the right moments. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The induced current would be much larger, so the magnet would take longer to reach the end of the tube because you'd have more force from the current pushing on the magnet. And then what if holes or slots were cut into the tube? How would this affect the ring currents in your model? The magnet would fall much faster because the induced current in the tube would be much smaller. The slots would break up the path for large continuous current loops, so the current would be weaker than a solid tube, and our model wouldn't have one continuous loop. It would have broken segments of loop, and with the breaks falling at the position of the holes in the tube. Thank you so much for watching.